In 1953, Eisenhower held his Atoms for Peace speech, in which he called for investment in civil uses of nuclear fission technology. This was followed by the founding of the IAEA and an increased interest and investment in using nuclear fission to generate electricity. In the late 50s to early 60s, the first commercial prototypes went critical, mostly using natural uranium and graphite as a moderator. The earlier reactors of the second generation were then mostly boiling water reactors and burned enriched uranium in its fuel rods instead. Enriched uranium has a higher concentration of the U-235 isotope, which is more unstable than the common isotope with 238 nucleons and therefore easier to split. In boiling water reactors, water is pumped into the fuel chamber to cool the fuel and evaporate in the process. This steam then propels turbines to generate electricity. Eventually, the steam is cooled down by another water circuit, usually using water from a nearby river. The condensed steam can then be led back to the burning chamber. Other than as a coolant, the water also functions as a moderator, slowing down the neutrons. This is necessary because fast neutrons would practically be bounced off the heavier nucleus very quickly, making it unlikely for the nucleus to bind the neutron. This can be derived from conservation of energy and momentum, as well as the assumptions of a central impact and one of the spheres initially being stationary, leading to the following formula for the velocity of the neutron. This also tells us that for impacts with spheres of similar weight, the resulting velocity is significantly lowered, giving us slow enough neutrons to cause nuclear fission. Now that we can maintain a chain reaction, we also need to think about controlling it. This is done with control rods, which can be inserted as demanded and catch excess neutrons freed by the fission reactions, such that the net number of neutrons that can go on and initiate new fissions is equal to the number of previous fissions. A reactor in this state is called critical, as opposed to over or under critical states, where we have more or less neutrons respectively. We can also make use of the fact that most neutrons are released instantly when the nucleus decays, and only a very small number of neutrons are emitted milliseconds to minutes later. If the reactor is critical only because of those delayed neutrons, the power output changes slow enough to be controlled. Another useful effect is the decreasing efficiency of moderators like water that comes with increasing temperature due to the increased bubble forming. This is called negative void coefficient. By now, most reactors being built are pressurized water reactors. They are a little more complicated to build, but offer advantages such as higher moderator efficiency due to the increased density and less water evaporating at the top of the burning chamber, as well as reduced turbine maintenance since the steam for electricity generation is produced in a secondary water circuit that does not come in contact with the radioactive material. Other reactor types include Canada's pressurized heavy water reactors, where the heavier hydrogen isotopes increase the moderator's efficiency and allow for the use of natural uranium, or light water graphite moderated reactors and fast neutron reactors that are used in Russia, or the gas-cooled reactors from the UK and China.